as I told you earlier, that excess electrons and holes do not move independently of each other. And in this lecture, we will discuss the same concept and will develop the expression for effective mobility and diffusion constant through which both the excess carriers move. Now, we have a semiconductor connected to an external battery. We will assume that the width W of the semiconductor is very thin. Now, a high intensity photon beam is introduced in the middle of the semiconductor. The intensity is so high that we can consider the generation rate of electron hole pair is uniform along the width of the semiconductor. Since the semiconductor is connected with an external battery, resulting in the electric field which will force free electrons and holes to move in opposite direction like this. We will say this electric field to be external electric field. We have paused the movement of charge carriers to focus on a very important point. If the semiconductor was not having any external battery, then the charge carriers will be redistributed throughout the semiconductor because of diffusion only. However, when an external field is applied, the situation changes. As you can see, electrons as a whole move in one direction, whereas holes collectively move in other direction. And this grouping of electrons and holes in different parts of the semiconductor results in another electric field which we will call internal electric field. The direction of internal electric field is opposite to the applied external electric field. This internal electric field actually tries to bring back electrons and holes together. This is the reason why electrons and holes do not move independently of each other at non-equilibrium conditions. Obviously, the strength of internal electric field is very small compared to external electric field. Otherwise, we will be getting current out of the semiconductor charging the battery. So, from whatever we have studied till now, we can conclude that the strength of internal electric field is very small compared to external electric field, and the electric field which we use in equations like continuity equation and Poisson equation is actually the vector sum of internal electric field and external electric field. Now we are going to take a very specific case where excess free electron concentration is equal to excess hole concentration, meaning that the semiconductor strictly follows charge neutrality. In other words, we are simply assuming that the semiconductor is direct band-to-band type, and therefore the generation rate of free electron is equal to generation rate of hole, and we will represent the generation rate of both the charge carriers by the same symbol G. Similarly, we can write for recombination rate. For free electrons, we have the continuity equation like this. Similarly, for holes, we have the continuity equation like this. But we also know that delta P is equal to delta N. So, after replacing delta P with delta N in the continuity equation for holes, we will get let this equation be first equation and this equation to be second equation. We will multiply first equation with molarity of holes into concentration of holes and will multiply the second equation with mobility of free electrons multiplied by concentration of free electron, and after that we will add the two resulting equations. By dividing the whole equation with mobility of free electron into free electron concentration plus mobility of hole into hole concentration, then we will get this final equation is called as ambipolar transport equation. You can simply write d dash, where d dash is effective diffusion constant of excess charge carriers, which is equal to, by using the Einstein relation, we will replace mobility of free electron and hole with diffusion constant of free electron and hole, which will give the effective diffusion constant to be equal to, and we have U dash, which is the effective mobility of excess charge carriers, which is equal to, we have taken a general semiconductor. Now for p-type semiconductor, as we know that hole concentration will be significantly greater than free electron concentration. Therefore, in the expression for effective diffusion constant, we can ignore free electron concentration as the hole concentration is significantly greater. Similarly, in the denominator, we can ignore the term containing free electron concentration. The diffusion constants of free electron and hole does not vary that much as compared to the concentration of charge carriers. So we will get the effective diffusion constant for p-type semiconductor to be equal to diffusion constant of free electron. Similarly, for effective mobility, we have effective mobility will be equal to mobility of free electron. The same way, we can find the effective values of mobility and diffusion constant for n-type semiconductor. So, after observing the values of effective mobilities and effective diffusion constant for n-type and p-type semiconductor respectively, we can say that at low level injection for an extrinsic semiconductor, the effective values of ambipolar diffusion coefficient and ambipolar mobility coefficient reduces to minority carrier parameters. Keep in mind that the effective mobility for n-type semiconductor comes out to be a negative value. Actually, the ambipolar mobility term is associated with carrier drift. Therefore, the sign of the drift term depends on the charge of the particle. So, for n-type semiconductor, the equivalent ambipolar particle is negatively charged. I have never seen any numerical questions from this concept coming in any competitive exam. And as per me, this is the highest depth from where questions can be framed. But still, it is quite an interesting theoretical point that the excess electrons and holes actually don't move with their respective mobilities and diffusion constant.